You may be somewhat familiar with the whorl-toothed sharks of the Carboniferous thanks to its most famous member, Helicoprion. What you may not know is that the group is extremely diverse and long-lived, only dying out in the early Triassic. One of these buzzsaw sharks didn't have a buzzsaw at all. In its place was a V-shaped pavement of bumpy overlapping teeth between a beaked mouth, but that is what made it survive the Permian mass extinction. Meet Fadenia. The major group that makes up all living sharks and their closest relatives is the Selachomorpha. This massive group has been around since the Triassic, when it began to diverge with the Batoidea, the rays. All modern sharks belong to the Selachii group, and this group only showed up during the early Jurassic, though it remains a possibility they were around earlier than this. This is just the earliest fossil record so far known. As such, other fish were taking up the large meso to apex predator spots in the ecological hierarchies throughout the world's many changing oceans. Eugeneodonts were this group, and came in all sizes, from small shark size to bigger than great whites. The Eugeneodontida is an extinct group of cartilaginous fish that not many people know about. They had tooth whorls in both jaws, or either upper or lower jaws, and their pectoral fins were held up by long radial bones. They likely didn't have pelvic or anal fins. These critters are most closely related to the ratfish of today, as they are members of the Holocephali. This means they are technically not sharks. However, many convergently evolved similar body shapes, adaptations, and feeding niches to sharks, and have therefore been informally referred to as sharks. They lasted from the Carboniferous period to the early Triassic, meaning they somehow survived the worst mass extinction of all time. Members of the Eugeneodontida are further divided into different families. The best preserved members that have been found are usually found to belong to the groups Caseodontoidea and Edestoidea. All Eugeneodonts are thought to have been obligate carnivores, meaning that they could only eat meat. Each genus had its own way of eating, geographic range, and prey items. The last of these critters started evolving away from the elaborate whorls of teeth of their Carboniferous and Permian predecessors, adapting their jaws into flatter, thinner, and more stretched out, beak-like jaws of bumpy, overlapping, but still recurved conveyor belts of teeth. One such form was Fadenia. Fadenia crenulata, 1932. The members of Loge Koch's Danish East Greenland expeditions of 1926-27 and 1929 collected numerous fish remains from marine Permo-Carboniferous rocks of Cape Stosch and to a lesser extent from other localities in East Greenland. The first fossils of Fadenia were discovered and written about in the periodical Meddelelse om Grønland in 1932 by the ephemeral Danish vertebrate paleontologist Ejil Nielsen. After studying the upper Permian beds of Cape Stosch in the fjord of Godthab Gulf in King Christian Excellent, Greenland, he had joined at the beginning of the 3-year expedition to East Greenland. In his 1932 work, Nielsen described 2 new genera and 4 new species of fish, one of which was Fadenia crenulata, with the genus named in honor of Dr. Gunnar Seiden Faden, and the species referring to the scalloped or notched nature of the mouth. This critter is abundantly represented by teeth from all parts of the kisser and by specimens with teeth in association. Nielsen found that Fadenia is an edestid fish, similar to Campotus and Helidus, having a row of bilaterally symmetrical symphysial teeth and numerous transverse lateral rows of asymmetrical and variable teeth. You may be aware of Helicoprion, the buzzsaw shark. This critter had just a single row of teeth overlapping one another in a conveyor belt that brought teeth forward in a spiral ammonite-like shape. Fadenia differed here in having multiple teeth to either side of the center whorl. Nielsen considered Fadenia the most primitive known edestid, and he did not believe that Protodus of the Lower Devonian was an edestid. Fadenia is also represented by a crushed skull from which few features can be determined. Since it was first named in 1932, plenty more remains were discovered. The well-preserved material from the marine Permian beds of East Greenland includes the pectoral fin, shoulder girdle, the first dorsal fin, and the caudal fin, making it one of the best known of the odestoid fish ever found. It helps to flesh out the rest of the huge family and provides an immense level of insight into what these shark-like shark cousins were doing in the world's various past oceans. Analysis of the pectoral fin material by Sven Erik Bent Almgren in 1967 enabled interpretation of some general traits concerning the musculature and the nerve supply. It was evident to Bent Almgren from the material he analyzed that the scapulocoracoid is both an abdominal and thoracic division, meaning that the bones resembled those in the arthrodires placoderms, like Dunkleosteus and the modern raisin skates. Expanding on this, the scapulocoracoid, the shoulder and chest bones that anchored the pectoral fins to the body, have a well-developed high scapular portion and a strong coracoid portion of which the ventral-medial part is forwardly directed. All of this suggests that some reduction in size of the front of the fin in proportion to the rest of it has occurred. The fin is made up of 19 long, unsegmented radial bones and a series of at least 6 elements that form the base of it, where it attaches to the shoulder. It's the remains of this genus, which are unusually well preserved, that are used to justify a lack of pelvic or anal fins in the rest of the Eugeneodontida. In those Fadenia specimens with soft tissues preserved, no pelvic nor anal fins are intact. It's possible that they fell off prior to fossilization, but that seems unlikely considering the near-perfect preservation of the rest of these specimens. It's a possibility that Fadenia was simply weird in this respect. Fadenia gigas, Eaton, 1962. Then, in 1962, Theodore Eaton published a study in the University of Kansas Museum of Natural History's publication on the teeth of the edestid sharks, naming a new species of Fadenia in the process. He described specimens KUVP753 and KUVP102, which were 2 symphysial teeth that are in place in a chunk of jawbone. It was found 4 feet, 1.2 meters below the top of Cherokee Shale, Lexington Coal, Lower Pennsylvanian, at Lucas, Henry County, Missouri, at some point in the past by someone, both of which remain unknown. Eaton notes that the teeth of these specimens are smaller than those of the holotype described decades prior. The height of the more complete tooth is 79 millimeters, not including a small part of the tip that is missing, and it's about 45 millimeters wide. The folds of the frontmost and backmost margins are farther apart and less numerous than in Fadenia crenulata, but the general shape and the pattern of folds and ridges on the surface closely resemble it. The specimens probably pertain to different regions of the symphysial series, but there is no evidence to show whether the series formed a simple arch or a spiral. The former, to judge from Nielsen's Fadenia crenulata, is more probable. The shark from which they came must have been large, perhaps 4 or 5 meters in length, to accommodate a series of such massive teeth and their counterparts in the opposing jaw. So, Eaton named the new species Fadenia gigas, with the new species name meaning giant. Neither the orientation of the Helicoprion spiral in the animal that carried it, nor the relationship of this curious device to the symphysial series in other edestid sharks seems to have been stated convincingly. In the more generalized members of the family, Campodus and Fadenia, it is clear that in the lower jaw, at least, a median row of teeth curved forward and outward, that they represented a growth series, and that the more lateral teeth were also arranged in series that curved up and out over the occlusal surface of the mandible. Whether these also were growth series is not entirely clear, but the manner of their replacement may not have been the same as in most sharks. The symphysial and lateral teeth in Campodus and Fadenia are not greatly different in structure. A growth series in the modern shark Lamna shows the usual method of growth and replacement, the largest teeth being those that have become functional and that will presently be lost. It's honestly kind of difficult for me to get a good mental image of the symphysial teeth whorls of Fadenia, specifically because in all of the papers I've read in researching this animal, no one ever provides a clear and concise diagram like they have done with Helicoprion or Adestis. It's like all of these authors had no hypotheses whatsoever and didn't care if there were people reading their work that have a hard time visualizing things.
Come on, stop whining.
Except, of course, for J.A. Moy Thomas and R.S. Miles in their 1971 revised publication of the massive Paleozoic Fishes textbook, in which they provide a quick and incomplete drawing of the tooth row, showing that these animals had the exact same type of laterally compressed teeth as Helicoprion and cousins. But the crown was shorter, rounder, perhaps meaning that Fadenia weren't piercing prey as much as their cousins were. What was that prey? It's hard to say. The Adestids provide the main exceptions to the general durophagous mode of life of holocephalans, the greater order to which they belong. This order includes nectonic species, which are marine and freshwater organisms that can swim freely and are generally independent of currents, ranging in size from microscopic organisms to whales, with a shearing dentition, which suggests a predatory mode of life. Nevertheless, even here, there is a tendency to durophagy, or the consumption of hard foods, and stomach contents of brachiopod shells have been found in Fadenia, so it can at least be assumed that these critters were munching on hard-shelled brachiopods, but anything else remains a mystery. They may have been able to eat all sorts of things, making them generalists. That may have been what made Fadenia the ultimate survivor of its group. A brand new species was identified in the late 2000s that pushes this group's existence over the Permo-Triassic boundary. Fadenia euroclasmato, Mutter and Newman, 2008. The highly specialized Eugeneodontid sharks are predominantly known from the Carboniferous and Permian. They are practically unknown from the Triassic. Zhang, 1976, reported a partial tooth whorl from the lower Triassic of western China, and one dentition fragment has been described from the earliest Triassic of Greenland by Nielsen in 1952. The skeletons of all adestoids are believed to have been very poorly calcified, even at their latest stages in life, and the anatomy of the skull, skeleton, and teeth can only be partly reconstructed by careful comparison of numerous fragmentary specimens. It is also assumed that the geologically younger, more advanced members were less extensively calcified than the geologically older, more primitive members, leaving an increasingly fragmentary evolutionary breadcrumb trail. In 2008, Raoul Mutter and Andrew Newman described the first articulated remains, partial teeth, and skeletal material of Eugeneodontids, definitely of early Triassic age. Previous reports of Eugeneodontids from the Triassic include only 2 poorly known species. Additionally, semi-recent reinvestigation of the Wurdy Creek Formation suggests that the most prolific fish assemblage described as early Triassic in age may in fact be late Permian instead. Raoul Mutter and Andrew Newman described 3 new specimens, TMP 8642-4, TMP 8742-11, and UALVP 46526 from the Wapiti Lake Fossil Site in Wapiti Lake Provincial Park, British Columbia, as the new species Fadenia euroclasmato. The new species name comes from the Greek euro for tail and klasmato for fragment, in reference to the tail preserved in the specimens. The Wapiti Lake Fossil Site yields a remarkable fossilogostata. The site, normally referred to as Ganoid Ridge or Ganoid Range, contains various localities where numerous fish fossils have been collected from outcrops of the Vega Froso siltstone member. Most vertebrate fossils from Wapiti Lake are preserved in exceedingly hard siltstone, predominantly with low carbonate content, or in dark, slightly bituminous, silty shales. Wapiti Lake and similarly timed localities contain the first Mesozoic strata, yielding articulated Eugeneodontids. The approximate early Triassic age can be given with confidence, although a more precise dating is currently not possible. The holotype specimen of this new species, TMP 8642-4, consists of 2 major parts, showing the partial front body and an almost completely preserved tail fin. The remains of the front body comprise the jaws and most of the visceral skeleton elements and parts of the pectoral girdle and fins. Meanwhile, specimen UALVP 46526 is the front chunk of the body with 2 pectoral fins. Vague outlines and surface depressions of the squashed skull, the sclerotic rings, part of the fin skeleton with several arches, and part of the tooth-bearing jaws, including a distinctive asymmetrical lateral tooth family. Only 5 to 7 teeth are visible. The weathered lateral teeth are very slender, oblong, and are conspicuously vaulted, with their highest elevation shifted towards the distal shoulder. In all, quite a good chunk of the animal's total anatomy is now known. This new species and the other Eugeneodontids described in the same paper by Mutter and Newman prove that several lineages survived the Permian mass extinction and recovered rather well and in astonishing diversity. The Helicoprion-styled spirals and the Eugeneodontids were long gone and have yet to show any sort of recovery into the Triassic, leaving only the Fadenia-type forms around to flourish. Due to the rarity and fragmentary state of preservation of most Eugeneodontid sharks, almost all aspects of tooth variation and anatomy are poorly known. According to the study by Mutter and Newman, major differences can be expected to occur in the arrangement and anatomy of upper and lower jaw teeth across the Eugeneodontid group as a whole. For example, the most complete dentition of Caseotus varidentis, the other new species named in this paper, shows striking discrepancy in the ornamentation of the upper and lower jaw teeth. The lower jaw teeth whorl of Caseotus and Fadenia would actually not act against teeth embedded in the upper jaw, but against teeth of an additional cartilage in the upper jaw or against teeth embedded in the underside surface of the very tip of the skull. In any case, the generally accepted reconstruction of the upper jaw tooth whorl as a functional tin can opener suggests a solid thing in the upper jaw for the lower jaw's symphysial teeth whorl to act against. What does this mean for the Great Dying? The Permo-Triassic boundary has long been held as the turning point in environmental history due to magmatic events, paleoclimatic change, seawater isotope changes, magnetic polarity shift, and proposed biota extinctions. Aside from the formation of the planet, this was the time in which it was almost like hell on Earth. The discovery of this group of cartilaginous fish in surprising diversity in the open marine early Triassic is set against this global picture. While many marine groups dwindled or became extinct towards the boundary, the presence of Eugeneodontids in the early Triassic of Western Canada in relatively high diversity suggests this group was much less affected by the major environmental turning point than previously believed. There are no major signs of extinction or decrease in body size of the group as a whole. It has been suggested this would have occurred during the recovery phase due to dwarfism and has semi-recently been shown for an isolated group of stem ray fin fish and was also documented in clams. Although the evidence does not yet allow precise assessment of relative diversity of this particular group during the entire Permo-Triassic turnover, these new findings support the view that the marine and Permian extinction event was highly selective. As Mutter and Newman write, the reconstruction of outlines of Pangean subcontinents and borders of Triassic marine habitats and their interconnections is problematic, even though continental plate movements following the breakup of the supercontinent Pangaea at the beginning of the Jurassic are fairly well understood. It's generally assumed that, according to the theoretical computer fit in which the relevant coastlines of today's continents are displayed to match perfectly, there were no apparent seaways present. For instance, between the Americas and Africa, or that there was no passage between the Proto-Atlantic and the west coast of Central America, connecting marine realms of the southern and northern hemisphere. The fact that we find similar faunal assemblages in both hemispheres, known as cosmopolitan taxa, exceedingly early in the Triassic, is normally explained as rapid dispersal events in impoverished habitats following the Great Extinction event. Paleoichthyology is capable of providing important contributions to more accurate delineation of ancient coastlines, because fish fossils are ubiquitous and often identifiable once a taxonomical framework is in place. In addition, certain late Paleozoic to early Mesozoic sharks were stenohaline, able to tolerate only a narrow range of salinity, like the Eugeneodonts. while some were euryhaline, able to tolerate a wide range of salinity, like the Hybodonts, and some were even freshwater dwellers, like the xenocanths. They are all, therefore, excellent indicators for paleoenvironments. But should we continue to observe a rising number of Lazarus taxa that disappear for one or more periods from the fossil record only to appear again later, in even earlier stages in the early Triassic, we may be forced to think about alternative explanations for the reappearance of taxa, and we'll have to attempt a quantification of the early Triassic sedimentation rates and their bearing on the rock and fossil gap. Recent research confirmed that the Induan, a stage of the Triassic period from 252.2 million to 251.2 million years ago, represents an extremely short time frame during which a smaller volume of sedimentary rock and hence fossil preservation may be expected. The pre-breakup phase of Pangaea, the Triassic period, is particularly interesting because it spans a time frame that holds the key to understanding Mesozoic and even living biotic diversity. From today's perspective, it seems improbable that global environmental changes on the scale of the Permo-Triassic boundary event or the Jurassic-Pangaea breakup event have been paralleled by an event comparable in significance during the Triassic. In other words, there was nothing cataclysmic going on during the Triassic itself. The time period was bordered by huge and immense cataclysms. Turnovers in faunal composition also occurred during the Triassic, and the causes for these allegedly minor changes may no longer be negligible for reconstruction of the Triassic recovery scenario. Establishing a temporal sequence of small-scale environmental changes is a necessity in identifying more localized turning points and Pangaean history that clearly pre- or clearly post-date the Permo-Triassic boundary. Only this data will provide a more detailed scenario of late Paleozoic to early Mesozoic paleobiogeography and disappearance of certain groups of vertebrates. It may be concluded that although environmental and faunal changes occurred during the Triassic at a smaller scale, these events may not necessarily have had a less severe effect on the faunal turnover. The importance of including detailed alpha taxonomical studies of lower Triassic fish remains when interpreting the scenario of the Permo-Triassic faunal turnover can hardly be overestimated, because the assessment of changing diversity is always based on taxonomy and not on the fossil record itself. It is likely that poorly preserved fish groups such as Eugeneodontids tend to be overlooked due to the lack of an established taxonomical framework. From this perspective, the Eugeneodontids are an extraordinary example, because not only has their stratigraphical distribution been underestimated, but also their diversity and geographical occurrence, apparently mainly due to the lack of appropriate preservation. Eugeneodontids are most probably strictly marine and highly specialized fish that are now known to co-occur in astonishing diversity across the Permo-Triassic boundary in the eastern Panthalassa and in the Proto-Atlantic Oceans. The single find in the eastern Paleotethys further expands the Eugeneodontids' strato-paleogeographic distribution. Future investigation of the undescribed Eugeneodontid material from the Permo-Triassic of East Greenland may significantly amend the understanding of the paleobiology of these sharks. It is also possible that Permo-Triassic Eugeneodontid oral teeth remain unidentified in various collections because their dental remains were previously not expected to occur in the Smithian, and because their minute distal and some of their lateral teeth are not easily distinguished from other non-Eugeneodontid shark teeth. Apart from these serious difficulties in accurate dating of classical late Permian and early Triassic fish sites, there are a number of other uncertainties linked to that particular fossil record in general, and to taxonomy and phylogeny of organisms across the Permo-Triassic biotic boundary transition. These problems are reminiscent of those encountered when interpreting the Cretaceous Paleogene biotic transition. In the case of relatively high faunal diversity in a geographically remote area, and in stratigraphically close proximity to the boundary, a peak in diversity would be interpreted as a biotic refugium following the extinction event. This scenario would be likely to change with a more complete record at hand, and does not explain the occurrence of archaic, taxonomically diverse sharks in an open marine habitat during the early Olenekian stage of the Triassic. For more interesting stories about nature, the history of life, or what goes bump in the night, subscribe, like this video, drop a comment in the comment section below, and hit the bell icon to stay in the know with everything Edge. Thanks for watching.
Mm-hmm.